All right, hello everyone. I'm excited to introduce Glenn Kasten, who works at Google at the Android media team, and Sanna Wager, who is doing her PhD at Indiana University Bloomington, and also works at Google. And they're going to talk to us today about analysis of real-time audio performance logs. So give them a warm applause.
Thank you. And the work today was also partially done by Nico Roulette, who was an intern last year, and he's returning as an intern this year. And Sanna, can you add a little bit more color about your work?
Yes, so I'm doing a PhD in music informatics. So I'm looking at audio quality, audio signal processing, and combining information from many different recordings.
Thank you. So we're going to use as examples today audio performance on Android. And Android has a reputation for performance, not always the best, but we're definitely making a lot of progress in performance, and the work you're going to see today is how we've been improving performance. Even if you're not interested in Android performance, I believe that the information that you can learn today will be really helpful to you on other platforms, both on desktop and mobile, and also in your own apps, because many of the techniques we're going to show today are not at all specific to Android or to mobile platforms. They also apply to applications. So, first of all, there are 2 rules, so I've heard, to being creative on mobile. And the first rule is you have to wear black.
Check. I've done that. This is from my senior recital. I was playing some CPE Bach.
And then the second rule, of course, I already let this out of the bag, is people say that you can't create music on Android.
That's really sad. You work on Android, and there are billions of users.
Yeah, at least 1 billion. So this was me, and that's my dog Bella. And a user had reported a problem with a karaoke app, and they were complaining to me. And I ran into the same problem. So we're going to get a demo. Toke? Show us the problem. Let's hope this works. Okay. Can you show us the problem?
My life will never be the same.
My life will never be the same. 'Cause girl, you can't.
That's pretty bad delay.
Thank you, Tucker. So, which one's real? Okay, this one. So people were reporting latencies of like several hundred milliseconds. I saw one report that was up to 800 milliseconds, and that's, if you know audio, that's really difficult to achieve. You have to try hard. That's a lot of memory. No, but seriously, it was in the couple of hundred millisecond range when we started. And so this was back in 2011. And this was a huge impediment to being creative, especially with live performance, with not so much with composition, but performance with any situation where you have interactive music. Latency is not acceptable. So I started on this in February in 2011, and I thought, oh, okay, I can deal with this. I have experience with performance. I can handle this. Bella was there with me, and she said, oh yeah, you could do this. So after a few months, not a lot of progress, but I was still somewhat optimistic. I took up drinking white wine, and socially only at first, of course. This was the picture you saw earlier. Still no progress at this point. A few months later, the white wine was gone, and I was getting really frustrated. There was new hope after, in 2012, I discovered Cheerios, and it turns out Cheerios really can help with late night programming. For a while. And then I got angry again.
You look pretty terrible.
Thank you. My wife said so too. If you notice, Bella had abandoned me at this point. She gave up on me. So it just continued worse and worse. The latency was going down, but not enough. I was nowhere near our goal of the low tens of milliseconds. commentary.
I'm speechless with this picture.
Things are really bleak at this point. And this is where we are now.
But Glenn, you've worked on this problem for 6 years, so you must have made some progress.
Oh yeah, definitely. We have made a lot of progress. You may have seen the mobile audio quality index that JB showed earlier today. We are down in the low, very low tens of milliseconds on our best devices, but there's still a large number of devices out there that are way too high. And there's some other sad news, which is I reduced the latency, but now I've got another problem.
So, what is your other problem?
Well, I'm so glad you asked. Let me show you. I'm going to have to do this. Oh, you're going to see this. Oh, well. Just pretend you're not seeing this. Here we go. Here's the problem. Oh, we are not plugged in.
So Glenn is going to play some bassoon music. And so it's this Bach that was mentioned before. It has very drawn-out, smooth phrases. It was written for a flute originally, so.
Okay. And this is Sanna playing. So smooth. So beautiful. What's that? Is that you?
Doesn't sound too good.
You need to work on that bassoon. Oh, this is not what I wanted. You don't want to know about my workout plan. Okay. So now you know about my second problem, which is I reduced the latency, but
I couldn't find any issue in there.
But now we have glitches, and I'm sure you've seen glitches in the time domain. In the frequency domain, they're even worse. And in the audible domain, they're the worst of all. So what I discovered through these many, many years of laborious work on latency is that there's a trade-off between latency and glitches, that I could get either low latency and high glitches, or low glitches but high latency.
I'd rather have neither, I would say.
Me too. I think most of our users would too. So here's a real high-level view of latency. Basically, we have audio coming in, as Toko was doing over the microphone, processed by the app, and then it comes out, and then the time difference between those is the latency.
So could you explain more?
Oh, sure, if you want to. It turns out there was an intermediate step, and that's what I totally missed at the beginning of my work. It took me 6 years, I guess, to figure this out. But no, actually, it was a little bit less, but it still was quite a bit of work. There's something in the middle between latency and glitches, and that's jitter, and I'll explain that in just a minute here. So here's a real high-level view of the data pipeline. From coming in from the microphone, we have an analog to digital converter, a FIFO. This is usually a hardware component. It's like a first in, first out queue or circular buffer. Goes into a digital signal processor. That's not processing, that's processor. And then from then on, it's running on the main app processor of our mobile computer. We have the kernel, the framework, your application, et cetera, and then very similar on the other side. This was last year's model of phone that had a 3.5 millimeter headset jack. Yay! In the current year's model, which omits the headset jack, boo. Anyway, it's over USB. We now have additional latency from the USB controller. Fortunately, it's pretty small, but it is significant because, as you all know, digital tends to add more latency than analog stages. But what we're going to do is I'm going to go back to the previous slide just for explanatory purposes, because the USB part is not really relevant here. There have been a lot of complaints about the framework contribution of latency, which is things like the mixer. And so thanks to some great work by Phil Burke here in the audience, we've been able to eliminate the framework contribution to latency by getting rid of the system mixer when it's not needed. when you have basically only a single app playing. So we got rid of that. And this is available with a new option in Android Oreo 8.1, which is just coming out now. It's called exclusive mode. And that's able to get rid of one mixed buffer. So earlier I talked about some of the hardware stages, the analog to digital converter, the FIFO, the DSP processor, things like that. Those tend to be constant for a given hardware architecture, and we at Google are working very closely with our OEM and silicon partners to reduce the hardware contributors to latency. But you don't have much control of that from the application side. So I'm going to kind of skip that and focus on the software contribution, which is the other light blue sections. And again, assume for right now that we've removed all the framework contributions. So the big question then is, why is there latency of a given size in the software part? And this is where jitter comes in, and I'll explain how jitter affects that latency. So first a review, we have the fixed constant hardware, we have the variable software, of which there's two parts, the framework and then the rest of it. Okay? So most audio is processed in fixed units or quanta, also called pull sizes or buffer sizes, things like that. And it's typically some small number of milliseconds, maybe 2 milliseconds, 3, 4 milliseconds. Sometimes for convenience with transforms between between frequency and time domain, it might be a power of 2, in which case it's not always an exact multiple of 1 millisecond. Here I'm assuming 48 kilohertz and 4 millisecond buffers, so that's 192 frames each time. And the little arrow represents the start of a callback. And ideally, your application should be started on time, and then you have 4 milliseconds to do your work and provide the audio, and then it's time for the next one. For this to work, though, however, we have to start on time, and we have to finish on time. And starting on time is our job, the operating system's job. Finishing on time is your job. You have to do your work in time. And that means you have to take the exact same amount of time every time you run. And the CPU clock frequency has to be sufficient so that you can do that amount of work in time. For safety, it's always good to allow a little bit of slop at the end. Don't use every last microsecond up until the end. So this is the ideal. And if we look at that on a graph, we can see the callbacks over increasing time. The first callback, second callback, etc. And in terms of absolute system time, it's linear. So this is with no jitter. But in reality, we have jitter. And jitter comes from a lot of different sources, but the primary ones from the system point of view are either interrupts being disabled or preemption being disabled, or sometimes other tasks, either system tasks or application tasks. We do run with the real-time priority, so ideally these shouldn't happen, but the truth is they do occasionally. And then whenever there's jitter, then we have a late callback, and that means that you have less time to do your work, and so there's a chance for an underrun, which then results in a glitch. So again, there's variability in timing. You get late task wake-ups, or if there's insufficient CPU, late task completions. Then you miss a deadline, you get an underrun, and that's what sounds like the horrible bassoon music, which is not what we want. This is a made-up graph. It's not this simple, but you can cover up glitches and jitter by just making your buffer sizes larger. So that's where latency comes from. Latency is not the latency is an effect. It is not a cause. The true cause is jitter. So at this point, a good question to ask is,
Well, what can we do about this? Can we somehow log the data to understand it better?
what a great idea. I wish I'd thought of that. Yes, we can log. We can log everything. Log the everything. So the kind of things we want to log is certainly task wake-up times. That's probably the most important thing. Also task execution times. That's up to your application. We want to log how much CPU bandwidth we have available, what the clock frequency is basically. We want to log which CPU core we're running on, because ideally we would have CPU affinity, which means we're locked onto one CPU core, but in reality sometimes due to misconfiguration or other problems, we're floating from one CPU core to another, and that can result in additional jitter. And you might think of other things that you might want to log that are more application specific. For how to log, first of all, we need it to be very lightweight, non-intrusive. These are usually running on a real-time audio thread, so we don't want to do extra work that's not necessary. We certainly don't want to write to a file, call printf, things like that. Don't want to acquire mutexes, anything that could interfere. A good solution for this is to use lock-free, non-blocking algorithms and data structures. Timur gave a great presentation on this at ADC last year. I encourage you to see his talk on video. And then I also gave a related talk last year about circular buffers, which are one technique for doing non-blocking logging. You generally want to log a timestamp with every log entry, and the typical way of getting a timestamp is to call your operating system function, and some of these are cheap. They're designed to be really, really quick. However, other timestamp functions do quite a bit of work because they're trying to correct for clock drift or synchronizing with Greenwich time or things like that. So make sure you're using a cheap timestamp, and make sure it's a non-blocking timestamp, one that doesn't internally acquire a mutex. On Intel processors, there's a timestamp assembly language instruction that it has a lot of problems between cores, but if you're locked to a single core, it can give you a pretty consistent value. On Linux, there's something called VDSO, which is a particular implementation of getting the system time that is known to be low overhead. And then I mentioned that you can use a circular buffer. Circular buffers are great because they don't require any locks, and they have the advantage that the reader and the writer can be completely independent. You can log, and hopefully the reader keeps up with the writer, but even if it doesn't keep up, the writer can continue and will not be affected. So your audio will not be affected if you run out of log space for some reason. This is a particular representation that Nico developed, which we found is a really helpful way of storing data inside of your circular buffer. It has a type code that says what kind of log entry it is. You know, like this is a CPU core number, or this is a clock frequency, or a start time, something like that. And then how many bytes of data you have, the actual data, including the timestamp, and then the length at the end allows you to traverse the circular buffer in either direction, and if you get an overflow, you can recover from error, so you don't have to worry about loss of synchronization. So, with all these logs, the question, what do we do with them? You know, how do we process them? Circular buffers, as I've described, only work well with a single producer, a single writer. So we put each log into a separate circular buffer per thread. So for example, thread 1 and thread 2 might both be real-time audio threads, and they write into their own circular buffers, and then we have a separate thread, which we call the merge thread, which combines the data. It sorts them by timestamp into a single thread, into a single circular buffer that's ordered only by timestamp, and that has a mix of data from thread 1 and thread 2. Unlike thread 1 and thread 2, the merge thread can be a normal priority thread, and so it can use mutexes if needed. We also have a summary and analysis thread that looks at the logs and does the statistical analysis, and that's where Sanna will come in.
Yes, so now we have data. So we can see on the y-axis that we have multiple samples of system time between callbacks. So we can imagine if there was no jitter at all, we would just have a straight line but we see some variability. It's not necessarily a problem at this level, except, well, something happened towards the end, probably a glitch, because we had about 7 milliseconds between 2 callbacks, when typically we would have 3. So now we haven't actually improved performance, but we can start to maybe explain what is happening, or at least describe it. But you might have noticed in the previous slide that we just had 1/10 of a second of data. And already we could maybe see some trends, but on the other hand, they would be short term. So now we have 30 seconds of data, and already we can't see the samples anymore. We just see these blocks. So this is really redundant data. So now the question comes, how can we learn from this data? And can we maybe represent it in a better way? And yes, we might want to look at 10 hours of data. If we, say, play audio for 10 hours, can we even fit all of that in memory? So this is where the statistics analysis comes in, or actually data preprocessing. We need to think about how we summarize our data, what we want to keep and what we can discard. And if we do this preprocessing properly, we'll be able to learn a lot from our data. If we don't do it properly, we might get some misleading results. So, for example, the first thought that typically we have when we have a lot of data is, let's summarize it using the mean and the variance, and maybe take the minimum and the maximum, so we get some idea of the range. But in this case, that might not work directly, because typically we have hundreds of thousands or millions of samples that will be always centered around the expected value. So no matter what happens to the data, our mean will not change, and the variance also probably will stay the same. And for example, so in this data set for 1/10 of a second, we had one glitch. And with our summary statistics, we probably would ignore that, because statistics are designed to see what is typically happening and ignore glitches. But in our case, the experience between, or the difference in experience between hearing one recording with 1 glitch or 0 glitches is huge. So we need to look at these outliers and focus on them. And minimum and maximum do help us a little bit, but they don't tell us the whole story, because they won't really behave differently if we have 10 glitches or just 1 glitch. And also, sometimes we might have an app that produces 0 actual glitches, but in one case it has a higher risk of having glitches than another. So we want to look at these data points that are in between the expected values and the bad values. So how can we track these?
I wanted to give an example of this with the 4 millisecond buffers that I used earlier. Because of double buffering, you can be late all the way up until about 7 milliseconds, or 6 or 7 milliseconds without a glitch. And then it's only when you get to 8 that you get the actual glitch. However, by that point, it's too late. You really want to know not just when you get a glitch, but when you're getting near a glitch, which we call risk. And unfortunately, min and max don't capture the amount of risk that you have in your data.
So how can we measure risk and failure? So Nico and then I started with one way of compressing the data. So histograms. So now we took what was on the y-axis, put that on the x-axis, so we have the system time between callbacks. And then on the y-axis, we can see the number of times we observed all of these different time intervals. And up here, you see the absolute counts, but then the histogram itself is in the log scale, because otherwise these small values wouldn't even be visible. The ones in the middle would be so much larger.
And ironically, those small values are the ones we're most interested in. So we want to highlight those, and the log scale allows us to do that.
So this histogram comes from real-time analysis, but we wanted to look at long-term data. So that's where looking at offline data was useful. So this histogram is actually for 10 hours of data. Maybe Glenn can talk about this particular histogram.
Sure. This particular sample is from an audio system where the buffer sizes, instead of being 4 milliseconds, were actually 40 milliseconds, 10 times larger. And you might wonder, why would you use such a huge buffer size? You know, you're going to get terrible latency. And yes, it is high latency, but this was deliberate. This is for a music playback situation where the screen is off, and power consumption is far more important than latency. So in this situation, latency is actually okay. It's not a problem. But we're still using it as an example just to show what a histogram can look like.
And so with this new data representation, we can learn about the overall behavior of a device over a long period of time, and we can then try to explain where these side peaks come from. But we have lost some important information, like time resolution. So if we did have a glitch, when did it happen in these 10 hours? So clearly, this helps, but it doesn't really solve our problem.
So on the next slide, we're going to go into the, what Sanna just mentioned, which is identifying the time when a glitch occurred. I wanted to mention one more thing about the difference between the low power case and the normal case where we want low latency. Notice that there's quite a bit of jitter all the way up to 60, 70 milliseconds on one side and down to 20 milliseconds on the other side. Turns out that's a property of our scheduling algorithm. This is not a real-time thread here, so having that level of jitter is quite normal and quite acceptable. It's not a problem. On the other hand, compare that to the to this case where you can see the jitter is far, far lower. It's on the order of about half a millisecond, which is still more than we want, but it's nowhere close to the level we had before. The reason is because this is a real-time thread. Okay, so now I'll turn this over to you.
So here's data from an actual experiment trying to compare performance in 3 different scenarios. So in one case, the phone was just playing audio in airplane mode and otherwise inactive. In the second case, it was installing about 50 apps at the same time while playing audios. In the third case, dial tones were being pressed. And again, this is log scale data, so these values are pretty huge, 10 to the power of 12. And now we want to somehow be able to compare these 3 types of performance. We might notice that here the data is a little bit less spread, but the 2 others look more similar. So is there a difference or not? This is where visual inspection might not be enough to really know what's happening. And also, you might notice that we have these triangular shapes due to what Glenn described in the performance. But it's really hard to fit any traditional statistical distribution to this kind of data. So now we can think about how to further process or prepare our data for statistical analysis. So we come back to this histogram. What the values we're interested in are the high-end values. So there are a lot fewer of those than what we see in the center. So we can just discard the typical behavior and keep what we're interested in, so the high values. So the simplest thing to do is determine what time interval between callbacks is long enough that it would likely be related to a glitch. And then we go through our raw data and store the timestamps of all the places where that happened. And so we get this kind of glitch timeline. And this can help us see what happened. But on the other hand, again, sometimes we may just have 1 glitch or 0 glitches. So we're missing a lot of data in this case. We might want to just know sometimes whether there's any difference between performance or between the shapes of the 2 distributions we're looking at. So another way of compressing performance is to start with our raw data again. So here we have the time intervals. And then we decide what behavior is good and what's not. And we assign a different cost. So cost would be, in machine learning or statistics, what we want to minimize. And so we can define it any way we want. In this case, we decide that 4 milliseconds is a good value, so we assign 0 cost. 5 is less good, so we assign it a higher cost. 7 is even worse, etc. So once we've done this mapping, then we can take, say, 10 seconds worth of audio performance, or any time interval we want, and we sum up the cost over all those samples. So then we summarize 10 seconds of data with a single value. And if we have, say, 10 hours of performance data, or 7 minutes like we had before, we can get a whole series that summarizes our cost over time. So now our data is in a state where we might be able to run some statistics on it. So just a very brief overview of the structure of a hypothesis test. So suppose we're looking at tennis professionals, and we have a null hypothesis. So in this case, we might be looking at the ratio between left-handed and right-handed players. And so our null hypothesis is that 11% will be left-handed. And we base that not on any data we have about tennis players. We don't know much about them necessarily, but we know that that's the case for the general population. So now the next step is that we'll collect some data so that we can actually, try to see whether our hypothesis has anything to do with actual data. So now we look at 17 people, and we observe that 7 of these were left-handed. And so what we need to calculate is what is the probability of observing the data we collected if our initial hypothesis is true. And that gives us the p-value, somewhat infamous term, but it's still useful sometimes. So in this case, we get, using just a binomial statistical test, a very small probability of this being true. So we can say that given that our data is very different from our hypothesis, we reject our hypothesis. So probably the percentage is much larger than 11%. So that's an outline of a hypothesis test, but how can we apply this to the performance data? So first, let's look at the glitch data that we had before. So now, in this case, our hypothesis might just be that, so we have our 2 apps, or 2 different configurations on an app or on a phone, and we assume that they behave in the same way, so they have as many glitches, and any differences we see between them are just random noise. So what we can do is we take long-term performance for each app, and then we count for each case the number of intervals of 10 seconds that contained a glitch and all those that didn't. So we see there's a lot of good intervals and quite a few bad ones in each one. So is this difference significant or not? So again, we calculate the probability of getting these 4 values if app A and app B are the same. And it turns out that there's a pretty simple combinatorics approach. It's called the Fisher's exact test. That'll give us a very small p-value. So as long as we have enough data, we can then trust that this means that app B actually does not behave like app A.
I'd like to add one thing about the glitch. These counts, 50 or 90, might seem like huge numbers, for glitches, and yes, they would be if they were actual glitches. But in many cases, these are not true glitches. They're predicted glitches, or they're risk of glitches. So the nice thing about this test, and actually all of the techniques Sanna is showing, is that they can also be used to measure how good your system is behaving or how good your app is behaving, even when it's performing well. You can see differences.
But then we had the second scenario where our data was different. We didn't just have a 4 data point table. We had 2 different sequences. So again, we start with the same null hypothesis that app A and app B performed in the same way. And again, we have random noise. And for this type of data, we can use another test called Welch's 2-sample t-test. To get a p-value using Welch's test, what we have to do is get the means and variances. But this time, we're taking these summary statistics on the process data. So what we get is actually more meaningful. And then we can see that this formula, it should have a 2 here, is basically comparing the means and doing some standardization by the variances. And so let's look at Welch test clarified the performance in our 3 scenarios we looked at before, it turns out that actually the device had very different performance in the 3 cases. 1 over 10 to the power of 34. So basically we have 0 probability of the 3 devices behaving in the same way. So it's pretty easy to decide what we want to test for specifically to know whether there's a difference and then run this kind of analysis. But there are some cases where we don't really know what to test for. So suppose we're building an app and there might be some corner cases. When we use a specific synth, then we might get a glitch, and we don't necessarily know to expect that. So how can we, well, explore the performance of our app more generally to get this kind of data? So there's an approach called correspondence analysis. I won't go into the detail of how it's done for now due to time, but what it does is it'll take the same data as before, the cost sequences for as many devices as are given to it, and it'll create a really high-dimensional map of all the different well, apps or devices or configurations. And basically, the higher the distance between 2 configurations is on the map, the more different their behavior is. And then it'll find a plane through those high dimensions that preserves those distances as well as possible. So then we see this 2-dimensional map where we can look at how the different configurations are clustered. So for example, we might say that, oh, airplane mode was turned off on those 2 devices. So that seems to be of interest. But then what happened with that phone that's so far away from all the others? So that can help us know what to test for. We did mention machine learning also, so we can at least touch on that also. Let's say that we do have access to a lot more data. So for example, well, you need to ask users before doing this kind of data analysis, but let's say that you have hundreds or thousands of users on an app who are willing to share how many glitches they had and what their device temperature was and CPU load, any other features that might be of interest. And then the question would now be, how does a change in device temperature affect performance? So then using random forests or Poisson regression, there are other like out-of-the-package methods. It can be possible to, well, even predict how, for example, one change in one feature might affect the performance. So that could even be used, for example, if a user is about to change something in something they're writing using an app, and warn them that if you do this, you risk having higher glitches. So you might want to check some other configurations. Okay. So a few takeaways. So
here's where you should get your notebook and your pen. No, hopefully this will be on video, right? So you don't have to memorize everything. But this is the time to wake up, please.
So basically, from the statistics point of view, the key takeaway would be that that we need to think about our problem. So what are we trying to avoid? What scenarios are we interested in? What costs do we assign to various events? And based on that, we can decide how to summarize our data and how to also compress it further, just to not waste memory on performance logging. And then also we can think about what questions we have. Are we comparing counts of events or distributions, or do we want to explore the data? And based on that, then we have a pretty wide selection of tests we can use.
On the Android side, the takeaway I'd really like for you to remember is that there are a lot of Android users out there, and they would love to be creative, and they deserve to be creative. And so, yes, it's true that Android has had performance problems. It is getting better, but it's still not where we want it to be yet. But even in that current situation, there's ways that people can be creative, even on Android in its current state. You just need to know what the limits are and think about, be creative, be creative with creativity. It's like, how can we enable users to be creative in spite of these limitations? And also to know, well, these devices are more performant than these other ones, so we can do certain things on these devices, but not on other ones. And simultaneously, the Android team, Phil Burke and I, and the rest of the team, in conjunction with our device partners, are definitely working to improve performance. So I want to reassure you of that. The other takeaway that I'd really like you to think about is that regardless of whether you're using Android or not, the techniques we've described here, performance logging, statistical analysis, ML analysis, these things can apply in other situations. They apply to desktop, they apply to other mobile operating systems, they apply to your applications. So even if you're running on the world's best desktop operating system, whatever, that has perfectly stable performance, you can still hit all of these problems that we've described in your own app. So it's good to monitor your app's performance and see how close you are to the edge. The thing that's related to that is don't just look for failures. Don't just listen for pops and clicks, because by that time it's too late. You need to know how close you are to the edge, and monitor that. I'm thinking like, my child. I don't just want my child not to go over the cliff. I want my child to not get too close to the cliff either. So that's and it's really hard to see reductions in failure rate. If your failure rate is 0, you can't see it reduce. But if you're looking at risk, you can definitely see reductions. Sanna, do you want to read off all these titles for us, please?
You told me you wouldn't highlight that.
This is her brother. Okay. So, thank you all for coming. And I guess, do we do questions?
Yeah, we have about 7 minutes
Okay.
for questions.
Yeah.
All right, so please. All right, questions.
Do you have a demonstration of the result of these changes?
Actually, JB gave a slide this morning that demonstrated it. It went by really, really quickly, but it's the mobile audio quality index. The situation is right now that we have a few devices that are quite capable for the for best quality performance and creation. So that's the result. We were worse before. So it's not where we want to be. We want to have far more devices, but I believe that with these techniques and working with our partners, we can get more devices that are capable.
Just a quick question on the new API. Is exclusive, how different is exclusive mode from fastpath?
Let's have Phil answer.
Okay. He's referring to a new A-Audio API, which is an alternative to OpenSLES, and the shared mode goes through an audio service and a mixer, and the exclusive mode will bypass the mixing service. So if the mixer has, say, double buffered of 2 millisecond buffers, then you'd be bypassing 4 milliseconds of latency by going directly to the HAL. So what you're doing is the app is writing into a buffer, and the DSP or the DMA is reading out of that buffer. So it's sort of the minimal latency. If you're doing round-trip latency, then you may be saving 4 milliseconds on the output and maybe a couple milliseconds on the input path as well. So the round-trip latency, in some cases, we've seen 6 or 7 milliseconds reduction by switching to an exclusive mode on both input and output.
Any other questions?
Thanks for the talk. Just a really quick one. Do I understand correctly that the bottleneck is hardware, where like any improvement is now on new devices only?
So again, the question was, what are the bottlenecks? So there are I'll focus on bottlenecks of latency first. So there's a hardware contribution that tends to be a fixed, constant cost for a given design, and that bottleneck, the only way you can shrink it is with a new design or a change to the getting a different phone or the next year model or whatever. And that we are definitely working on, both in our own phones, our Pixel phones, and also working with our partners to share best practices on. So that's the bottleneck there. There have been new bottlenecks added recently, such as USB, and so that was kind of a mixed blessing, because I love the additional digital quality from USB. On the other hand, I don't like the additional latency that comes. So that's on the hardware side. On the software side, the main bottleneck in the system part of it is this jitter that comes from late task wake-ups, and it's usually, but not always, caused by Linux kernel performance bugs, where some random part of the system, it tends to often be Wi-Fi for some reason. Sometimes the fingerprint sensor can do that too. Will disable the interrupts or disable preemption for a long time, and that causes then the audio task to get woken up late, even though it's real time. That's one bottleneck. Another bottleneck, which we've had progress on recently, is when the CPU clock frequency changes inappropriately for audio. It gets decreased, maybe because we haven't had much audio workload recently, but then suddenly there's a huge increase in the audio processing, but it takes a while for the clock frequency to ramp up again. So there we've been working on better algorithms for picking the clock frequency so that we have a more stable bandwidth. Trying to think other bottlenecks. Certainly your own application is a bottleneck too. You need to think about how much digital signal processing you're doing and keeping it consistent. There was a talk just this morning about parallelizing your DSP using SIMD and avoiding branches. And those techniques will tend to keep your CPU load more constant. You definitely want to have consistent CPU.
So we need to wrap up, but I think you both are going to be here for the rest of the conference, right?
Yes.
So you can.
So will Phil and Don too.
All right, cool. So you can talk to these guys and ask all your further questions. All right. So one more applause for our speakers.